Okay, good morning, everyone. Today we'll look at example 5 for chapter 5. That's the last one. And in the interest of working through it efficiently, I have already copied over the annotations. So students who have the class notebook automatically have the entire solution. And so let me bring that up. And of course, you can take notes, as many notes as you want. So as we go along, I'm going to provide explanation. So specifically, you might want to note down those explanations, right? All right. So in examples 1 and 2, we looked at adding or summing up two voltage sources or two signals, right? The same technique can be applied if it's a current source. If you have two current sources, two or more current sources, you can combine them together by converting it into phasors. And then in examples 3 and 4, we looked at components, inductors and capacitors. Both examples refer to finding the current because you are given the voltage, you're given the impedance, and then you found the current. Now we combine everything together into one large circuit. Okay, one large circuit. So in this circuit, we have three components, R, L, and C. So this circuit can also be referred to as an RLC circuit. Okay, RLC circuit. And you have a voltage source, Vs of t, being applied to those three components. Now, as far as circuits go, this is rather straightforward. Okay. As a reminder, chapter 5, there is no new analysis technique. The analysis techniques are the exact same as what we learned in chapters 1 and 2. Okay. The math is new, but the analysis techniques are not. So the first step I always tell students to do is to draw out the equivalent impedance diagram. The equivalent impedance diagram is where we replace all components in that circuit with its equivalent impedance. Okay. Basically, it looks like any other DC circuit that we looked in chapter 2. Okay. Remember, the components are not AC or DC. It is the source that makes it either an AC circuit or DC circuit. Right? So the components are not AC or DC. It's the source that makes it AC or DC. So if you look at the circuit in isolation, what do we see? If nothing else was given to you about the circuit and just saw the circuit, you would think it's like a 3-resistor circuit with a voltage source applied to it. Right? So I always want to assure students, chapter 5 is AC. They look at differential equations, complex numbers. I like to lower the stress levels by repeating that it's not new analysis techniques. It's the exact same technique. And to apply those techniques, what you can do is draw the equivalent impedance diagram where every single component is replaced with its equivalent impedance. Resistor, of course, does not change. It behaves the same way for DC as it does. It behaves the same way for AC as it does for DC. Inductor is replaced with ZL, inductor impedance, and capacitor is replaced with capacitor impedance, ZC. Okay, so what do we see? Every single component is connected to the other components by only one connection each. So they are all in series with each other. We can see that the voltage source is also in series with those three components. So we can determine our approach based on that analysis. If it's a series circuit, we can reduce the entire circuit down to one single resistance. Or in this case, it'd be one single equivalent impedance. So we would find ZEQ similar to how we found REQ in chapter 2. Remember, chapter 2, the beginning of chapter 2 was resistors in series, resistors in parallel, and then combining a large resistive network down to one single REQ resistance. So we would take the exact same approach. We would take a large network of impedances and combine it to one single equivalent impedance, ZEQ, as seen by the voltage source Vs. Again, the key words, as seen by. You remove the voltage source from your analysis and you determine ZEQ between those open terminals. Okay, ZEQ between those open terminals. In this case, ZEQ is simply R plus ZL plus ZC. Let's take a pause. Let me know if you have any questions thus far. Does this make sense so far? Okay, so we draw the equivalent impedance diagram. We define our approach. We selected the approach as ZEQ, reducing everything down to one single equivalent impedance. So now we need the values for the individual impedances, ZL and ZC. For that, we need omega. And for that, we go to the source. The source value is given right here. We compare it to the standard equation of a time-varying voltage or time-varying sinusoidal signal. So Vm cos of omega t plus theta. From there, we extract the information about the three quantities. Vm, which is 100 volts, omega, which is 500 radians per second, and phase shift for theta is 30 degrees. If the source is not given in cosine, then you have to convert it to cosine. So convert sine to cosine. Otherwise, you cannot write out the phasor. Okay. So again, if the source is given in sine, you need to convert it to cosine. Okay. So now we can begin our calculations. Vm is 100 volts, phase angle is 30. We can directly write the phasor for Vs, right? 100 with an angle of 30. That's it. 100 with an angle of 30. If you had more than one voltage source in there, you would have to figure out a way to combine those if they are able to combine. Otherwise, we'd have to apply node voltage analysis or mesh current analysis. Same techniques, except complex numbers. So Vs is 100 with an angle of 30. Now we want to find the individual quantities for ZL and ZC. As equations go, you simply take the equations, plug in the values, and you find the answers. I'll explain what I have done here. Goes back to my calculator being old. I can perform polar to rectangular, rectangular to polar conversions, but I cannot program equations directly in there. So if I have to perform addition, subtraction, multiplication, or division, I need both. I need the values in both polar coordinates as well as rectangular coordinates. And again, as engineers, you should be aware of how to solve this. So this is an approach where you can solve this with any calculator, okay? You do not need a highly specialized programmable calculator. And that's why you see me finding the values for ZL and ZC twice. The first one is finding ZL using the polar coordinate system, omega L with the angle of plus 90. Second one is rectangular coordinates, so ZL is J omega L. Think back to page number 15. Page number 15, we talked about how the voltage for an inductor is 90 degrees ahead of its current. So the impedance for an inductor is always plus 90. For an inductor, the impedance is always minus 90 because the voltage is always 90 degrees behind the current. So the equations are standard. Omega L with the angle of plus 90, ZC is 1 over omega C with the angle of minus 90. Rectangular coordinates, ZL is J omega L, ZC is 1 over J omega C. Did I do the derivation for 1 over J? 1 over J is, as a short explanation. You multiply and divide by J. That gives you J divided by J square. J square, of course, is minus 1. And you get minus J. So the reciprocal of the imaginary number is the negative imaginary number. 1 over I is minus I. 1 over J is minus J. Hence, 1 over J omega C gives you minus J50. If you convert minus J50 to polar coordinates, you get 50 with the angle of minus 90, pointing straight down. Inductor pointing straight up. Let's take a pause. Let me know if you have any questions. Any questions? Anyone? Online students, if you have questions, please just speak up. Please interrupt. If you type it in the chat window, I probably won't see it. Does it make sense so far? Okay. So once you have ZL, ZC, you simply find ZEQ. If the circuit is in parallel, you apply the reciprocal method. Here it's in series, so you simply add them all up. R plus ZL plus ZC gives me a ZQ of 100 plus J100. At the same time, I know I need to perform a division, so I will find the answer for ZEQ in polar coordinates also. 100 plus J100 gives me a magnitude of 141 and a phase angle of 45. When the real and imaginary components have the same value, the angle will always be 45. Right? It has two sides of the triangle. Two sides of the triangle. So it's an isosceles right angle triangle. Means the angles will always be 45. So you have ZEQ. Well, from this point on, simple application of Ohm's law. You apply Ohm's law once to find the total current because the circuit reduces to this. You have a voltage source and you have ZEQ. So you have VS, ZEQ, and you have current I flowing through the entire circuit. That current I is the same for all four components, the voltage source and R, L, and C. It's a series circuit, so the current is shared by all four. Right? Going back to the original circuit, I is the same for all four components. So it becomes I equals VS over ZEQ. You perform the calculation, you get current I with a magnitude of 0.707 and a phase angle of minus 15. perform the inverse phasor transform, then you write out the function of current as a function of time, I of t. The frequency is not affected. Remember this entire chapter. Resistors, of course, behave the exact same way, so we don't have to worry about resistors. Inductors and capacitors affect the phase, they affect the magnitude, but they do not affect the frequency. The frequency remains exactly the same, which you obtain from the source. So 500 radians per second, omega stays the same. Oh, not there. Right here. Cos of 500t minus 15 degrees. Note the phase angles for the voltage and for the current. The voltage had a phase angle of plus 30. The current has a phase angle of minus 15. Plus 30 and minus 15. The resulting current for the source depends on the circuit configuration and the values of those components. It could turn out any angle. Okay, if you take simple Ohm's law, if you apply voltage of 10 volts to a resistor of 10 ohms, your resulting current I is 1 amp. So that current of 1 amp depends on the value of that resistor. Similarly, in AC analysis, the value of the voltage or current and the phase angle depends on the values of the inductor and the capacitor. And of course, how they're connected, whether they're connected in series or parallel or series parallel. Once you have the current I, you again apply Ohm's law, V equals IR, and you calculate all three quantities, VR, VL, and VC. Okay, VR, VL, and VC. The resistor voltage, inductor voltage, capacitor voltage, you don't need to perform any differentiation or any integration. You can simply apply Ohm's law and perform complex number math calculations, find the final answer. We can do so because I is the same for all. So think over that. Let me know if you have any questions. Any questions so far? Does it all make sense? An alternative way to determine the voltages would be to apply voltage division. The equations I have noted right here. I would strongly recommend students do this practice outside of class. You have the values, you have the final answers, and I provided you the equations. All you have to do is perform the math. Again, think back to chapters 1 and 2. It's a series circuit. When you apply voltage to a series connection of resistors, a fraction of the voltage appears across each resistor. Same principle here. You have an impedance, you have a voltage applied to these impedances. A fraction of that voltage appears across each impedance, and you can calculate it by applying voltage division. You will obtain the exact same answers. Okay, you will obtain the exact same answers. It wouldn't change. So VR is simply Vs times R over ZEQ. Okay, phasor diagrams. Phasor diagrams are a very powerful tool to graphically represent the voltages and currents in a AC circuit. If you remember last class, I said, if you wish to plot the phasor diagram, you are simply plotting out vectors. The only thing you need to plot or draw out a vector is the length and the phase angle. In this case, let's take a look at voltage Vs. What do we need? You simply take the phase angle first, and we draw a line approximately at that angle. And that's it. Mark the angle and note down the length. It's not to scale. It's not to scale. Okay. So Vs is 100 volts with an angle of 30. So approximately draw out 30 degrees, draw a vector, and mark it as Vs. And again, as I stated, this is not to scale. Then we can plot out I. This current I is common to all components. I is at minus 15. Phasor is a vector that's rotating counterclockwise in the first quadrant. So plus is always going counterclockwise, and minus or negative angles are going clockwise. So if the current is minus 15, you have to start from the real axis. It's going clockwise, means it's below the real axis. The minus 15 is right there. Magnitude of I is only 0.707. It is not even 1 amp. Okay, Vs is 100 volts. So technically, Vs should be more than 100 times as long as the current I. As I said, it is not to scale. VR has the exact same angle as that current. That current is shared among all four components. Resistor does not affect the phase of the incoming voltage or current. So the voltage for a resistor has to have the same phase as the current. So it also has minus 15. Plots on the same line. ZL and ZC are at plus 75 and minus 105. Because they share the same current, the voltage for the inductor and the voltage for the capacitor are exactly 180 degrees out of phase with each other. Inductor voltage VL is 90 degrees ahead of the current. Capacitor is minus 90, meaning capacitor voltage is 90 degrees behind the current. And because the current is the same for both, the phase for the voltage VL and VC is 180 degrees. Plus 90 and minus 90. Exactly opposite. If it was a different circuit configuration and they did not share the same current, then the phase difference would not be 180. It would be something else. Let's take a long pause here. Let me know if you have any questions. Yes. That is correct. So the question being asked is, resistor, does it have an angle of 0? The answer would be that it is correct, because resistor behaves exactly the same way for AC that it does for DC. So it would be more accurate to say it does not have a phase angle. Or if we say it has a phase angle, it has a value of 0. It lies flat on the real axis. Yep. All right, any other questions? Does the approach make sense? Do the steps make sense? Now, the approach here, of course, is straightforward because it's a series circuit. If it's a parallel circuit, you combine it differently. It's a series parallel circuit or parallel series, and the approach would be different. Okay, yes. Sure. We can go back to page number 15 for that. So the question being asked is about the phase angles for the inductor and the capacitor. So in an inductor, the current always lags the voltage. by 90 degrees because the current cannot change instantaneously. So the voltage might change instantaneously, but the current will change after that. So it always lags the voltage by 90 degrees. Impedance Z is V divided by I. When V and I are both complex numbers, phase angle for V divided by phase angle for I would be theta V minus theta I, which would always turn out to be 90 degrees. Capacitor is the exact opposite. Capacitor, the voltage always lags the current, and the current is always ahead, meaning the voltage is at minus 90 with respect to the current. And so when we take the impedance of a capacitor, it'll always be minus 90. So plus 90 and minus 90. But it's only specific to that particular component. Okay. All right. Any other questions? So let me talk a little bit about the lab. In this week's lab, which is lab 6, unless your lab is ahead, what you're doing is you're verifying KVL for an AC source. What you're going to do is this. You're verifying KVL for an AC source, okay? You're going to represent the voltages for an inductor and a capacitor and a resistor in vector form. And that's what you're doing. So, an ideal inductor, what is the resistance for this inductor? Inductor resistance is 0. Ideal inductors, RL is 0. However, real-life inductors have resistance. They are made out of a conducting coil of wire. Any current-carrying conductor inherently has resistance, it has inductance, and it has capacitance. The values of these R, L, and C component, R, L, and C phenomena quantities do not rise to the level of interference, right? However, when it's an inductor that is made out of a coil of wire, that coil of wire has resistance. Going back to, let's see, the definition of resistance or the calculation of resistance, it is given by rho, the Greek letter rho, L over A. Rho is the resistivity of the material. It is a material property. Okay, rho L over A. So if you have a wire, and this is a enlarged description of a wire, this would be the total length of the wire from end to end. And this is area, cross-sectional area of that wire. Directly proportional to L, inversely proportional to A. Meaning the longer the wire, the higher the resistance. The thinner the wire, the higher the resistance. So if you have an inductor that is made out of very thin wire in a large number of turns, then the resistance would increase proportionally. And if you remember chapter 3, I showed you certain examples. Remember, there was a small inductor which had a high number of turns. Inductance, if you remember, is directly proportional to the number of turns, meaning the larger the inductance you want, the higher the number of turns you would have in your inductor. But the number of turns increases, meaning the length of the actual coil is increasing. So it's a trade-off between having a large number of turns, meaning higher value of inductance versus higher the resistance. If you take this inductor and you measure the inductance between A and B, it would give you some value for L. If you take the exact same inductance and you measure the resistance between A and B, it will give you some resistance value also. that is physically part of the exact same component. You cannot separate those two out. The resistance and inductance measured between A and B is exactly the same physical component, but two different electrical quantities. Does that make sense? And so electrically, we can represent it as a inductor in series with a resistance between the terminals A and B. That's what it is. The inductor will have a value of L. RL here notes the series resistance of that inductor. It's not low resistance, it's the inductor resistance. Yes. Yes, because it's cross-sectional. So the question being asked is about the diameter of the wire. Oh, the spiral, the core. No, it doesn't have any effect on the resistance. So the question being asked was about the diameter of the spiral coil. That is a part of the inductor equation, but not of resistor. So what was I saying? Oh, the inductor. So again, physically, it's the exact same component. Electrically speaking, we can model it as an inductor in series with a resistance. Does that make sense to everyone? And there is a term that we use to describe the quality. Q for quality. So Q is the quality factor of the inductor or capacitor. And it simply states that mathematically, it simply states it's the ratio of the inductor reactance, XL. Okay, inductor reactance, XL, to the series resistance, RL. That's it. Inductor reactance, XL, to the ratio of RL. For an ideal inductor, RL is equal to 0. Hence, quality of an ideal inductor is infinite. In real life, high quality inductors typically have RL less than 5 ohms. 5 ohms. So in today's lab, not today, so this week's lab, lab 6, what we do is we simulate a bad inductor. Okay. So the labs are written when we didn't have low quality inductors. We only had high quality inductors. And so what we would ask students to do is you would add an external RL. You would add an external resistor in series with your inductors, with your high quality inductors, to simulate or model a bad low quality inductor. We have since acquired low quality inductors. Okay. So depending on the lab components you're using, you may have to either add this RL or ignore the RL. In my labs, I specifically request I want low quality inductors, so we don't have to add this connection. It depends on instructor to instructor, depending on who is your instructor for your lab. Yes. Yes, that's what we're doing. We are simulating a bad inductor. Otherwise, we would not be able to perform that experiment. Okay. And then we do that again. So if your instructor requires you to add a RL to a bad inductor, then you'd have two resistors in series. One is internal to the inductor, one is external. Okay, so keep that in mind. So again, Q or QL in this case, quality of the inductor, is the ratio of its reactance to its resistance. And when you measure the inductor value on your LCR meters, it will give you the value of RL. It'll also give you a value of Q. It'll give you a value of Q. The low quality inductors have a value of around 2 or 3. And because it's a ratio of reactance to resistance, ohms to ohms, it's dimensionless, doesn't have any units. It's simply a ratio of reactance to resistance. Any questions? No questions? Okay. All right. Then we can consider chapter 5 to be at an end. Okay. We can move on to chapter 6. One more point about the example we just did, example 5. The approach we chose was combining into one single impedance, ZEQ, because it's in series. If it's in parallel, your approach would be different. You would still combine in ZEQ, but slightly different. It's a series parallel circuit, or if you have more than one source in there, your approach would be different. Okay. So again, draw out the equivalent impedance diagram, analyze it as you were analyzing a DC circuit, and then do the math afterwards. Okay, frequency response. So in this chapter, we have to adjust our thinking a little bit. As the title of the chapter suggests, we are going to use multiple circuits, and we'll study the response of these circuits depending on the incoming input frequencies. So we're going to study the frequency response of multiple circuits. So before we do that, I always like to introduce the common signals that we use in everyday life. And by now, everybody should be able to answer the question, what is the frequency of the power outlet? 60 hertz. Outside of North America, 50 hertz. There are many various reasons for using different frequencies. 50 and 60 hertz power line frequencies are very, very low. Normal human hearing range is typically said to be between 20 hertz and 20 kilohertz. Most people like me probably can't even hear anything between 100 hertz to maybe 14 or 15 kilohertz. Okay. That is still considered to be a low frequency. Okay. In real life, our frequencies go in like millions and billions of counts. As an example, radio stations, AM and FM. AM stands for amplitude modulation, FM stands for frequency modulation. AM radio stations broadcast at certain frequencies so as to not interfere with other signals. AM radio stations broadcast in the kilohertz range, thousands of hertz. Okay, thousands of hertz. 680 AM is the broadcasting frequency of that particular radio station. So 680 stands for 680 kilohertz of frequency that the radio station is broadcasting. 101.7 FM, the station is broadcasting at 101 megahertz of frequencies. Television stations, again, sometimes it says WKR 690 WKRD, and that is the broadcasting frequency of that television station. Mobile signals, satellite communications, they're all broadcasting in gigahertz and terahertz range. Common examples that you use every day, your cell phones, and then your wireless routers. These frequencies are known as airwaves because they are sending waveforms or wave signals over the air. So, like with anything in life, it's all controlled by the government of each country. The government controls the land, they control the seas, and they control the air, right? In the US, it is controlled by FCC, Federal Communications Committee. So the airwaves basically range or comprise of a certain number of frequencies, and it's pretty standard across the world. So AM and FM frequencies, television frequencies, they are all the same particular band of frequencies all across the world. Each country's government determines which frequencies they're going to use. And they auction off these frequencies, meaning the right to use a particular frequency is auctioned off by every government. These are very valuable. The costs of owning these frequencies for a certain period of time runs into billions and billions of dollars. That's how the government makes a lot of money. So AT&T, Verizon, and T-Mobile, they are the only three actual carriers that have physical networks in the United States. Alaska is different. Puerto Rico is separate. Okay? Alaska has its own company. And then Verizon, AT&T, and T-Mobile, they actually have tie-ups and they buy allocations from that local companies, but they don't have any physical infrastructure. These three companies have physical infrastructure in the continental United States. And every few years, they bid on the right to use a particular frequency spectrum. The reason is some particular frequencies are able to travel further than others. Some of them are able to penetrate through walls, some of them not so much. So if you had Sprint, like I did for a number of years, Sprint was infamous because they were broadcasting at certain frequencies that could not penetrate through walls very well. They could penetrate through walls, but not very well. And certain frequencies can, certain frequencies can't. Especially if you have metal, like you have metal rebars to concrete walls, they will short out your signals. And so that happens. Anyway, coming back to the point. So these frequency spectrums are like highways. Each company will purchase this highway for a certain period of time, and then only their vehicles are allowed to travel through those highways. The reason is if you transmit at the same frequency, it causes interference. Okay, so if you have an FM station, and it's broadcasting at 101.7, if somebody's trying to listen to 101.7 and you set up an FM transmitter right where somebody else is trying to listen, and you broadcast something else exactly at that same frequency, then it's going to confuse that receiver. Instead of listening to the FM radio station coming to the air, they might be listening to what you are broadcasting. That is how wireless jammers work. That's why if you have a wireless camera system or a wireless router network, it's very easy. You simply set up your own transmitting station at 2.4 gigahertz or 5 gigahertz of wireless router, and your wireless network goes down. Nothing can work. Your cameras, your wireless cameras will not be able to communicate to your wireless router. It's very easy to do that. Okay. So scammers and thieves, that's what they do now. They buy wireless jammers. If they know somebody's, the recent cases around LA, where lots of homes were broken into, they just keep an eye out on these, homes. As soon as the owner goes out, they have a wireless jammer. They go in there and they put these jammers in action. Signals from the wireless camera cannot reach the wireless router. Entire system is down. Anyway, I tend to go off on tangent because I love talking. Coming back to the main point. So how do we block these signals? Let's say you have an AT&T service. You have an AT&T phone. How does AT&T prevent Verizon phones from being used on their network? Well, they control everything, but they control it by using the feature of frequency responsive circuits, which is known as filtering. So what we're going to study in this chapter is electronic filters, electronic filtering. As the name suggests, it allows certain frequency or signals to pass through, and it blocks certain frequencies from coming through. So if you have a cell phone that is approved for use by AT&T, it has a filter at the front end. It is going to block signals from T-Mobile. It is going to block signals from Verizon. It's not going to allow them to enter that phone device. And also, if you put your hands up like now, our bodies are antennas. Our bodies can receive all the signals in the air, right? It can receive television signals, Radio signals, mobile, satellite, all signals are in the air around us. We are not doing anything with those signals, but our body is a receptacle for all of those wireless signals. Anyone ever use rabbit ear antennas for your televisions? If a signal is not coming out right, you can hold that antenna and the signal will turn, sometimes might turn all right. Is because your body is absorbing those signals. And now in conjunction with the rabbit ear antennas, the television signal is now stronger. Anyway, so there are circuits that will filter out unwanted signals, unwanted electrical signals. They are known as electrical filters, and that is based on the concept of the frequency response of inductors and capacitors. Hence the title of this chapter, frequency response. Okay, so from now on, we have to adjust our thinking a little bit. Okay, for this entire class, we have looked at in terms of individual wires and individual currents going through a circuit. Now we have to think in terms of input and output between a pair of terminals. It combines the positive and negative end of a source together to form a port, P-O-R-T. On one side of the circuit, we say that we are providing an input. We still have voltage and currents flowing through the circuit. But again, we have to adjust our thinking just a little bit because we're now going to think in terms of combined pairs of terminals. So you combine two terminals together, you form a pair or a port, P-O-R-T. On one side, we label it as the input port. On the other side of the circuit, we label it as the output port. The circuit can be referred to as a two-terminal, two-port network. Network is another word for circuit. So it's a two-terminal, two-port network. Okay. The output can be taken across any component. Could be a resistor, could be a capacitor, could be an inductor. Does not matter. But you would be taking the output across, across a component, meaning you have a pair of terminals, plus and minus. Okay. So again, output port and input port. And we're going to look at the circuit as a sealed box. Okay. So in the first portion of this chapter, we will look at a circuit as a box. We don't know what that circuit is. We don't know what that circuit does. Okay. In general, we can use the simplified diagram to describe what a filter might do. Signals are comprised, as I said, signals are all around us, right? So this is, let's say, a simplistic representation of a signal that is comprised of two components, V in 1 and V in 2. A filter circuit comprises of resistors, inductors, and capacitors. Resistors do not do anything except change the amplitude, right? You have the y-axis, the amplitude of the signal, and it changes. Resistors reduce, and so it reduces the amplitude. Capacitors and inductors will reduce it and will also affect the phase. The frequency is not affected. The frequency is not affected. It's not changed. Keep that in mind. Inductors and capacitors and resistors do not affect the frequency. However, depending on the impedance of the inductor and the capacitor, they will block certain frequencies from passing through, and they will allow certain frequencies to go through. So in this case, depending on the frequency, V in 1 is allowed to pass through and is actually made stronger. It is amplified. It is made larger. Whereas V in 2 is actually reduced. So the effect of a filter is such that it breaks down the components, affects each component differently, and then you combine it together and send it to the output. That's not exactly what it does, but this is a Again, a simplistic explanation, simplistic representation of how it could work. And then this is something I came up myself. So I named it after myself. Not really true, obviously. I've never been able to find a definite answer of why it is called h of f. Okay, but it is known as h of f. It stands for the transfer function. It simply is a quantity that describes how the input is transferred to the output. Hence the name transfer function. So far, we have looked at quantities as a function of time. What is this a function of? Frequency. Hence, frequency response. Mathematically, it is simple. H of f simply describes the ratio of V out to V in. How is the input being transferred to the output? V out and V in are phasor representations of your input voltages and output voltages. Hence, H of f is also a phasor, or not phasor, but it's a complex quantity. V out and V in are also complex quantities. So H of f is also a complex quantity. It has magnitude and it has phase. It's a ratio of voltages. So it is dimensionless. It has no units. So we'll end class here today. We'll pick up here again on Friday with an example. There's only, there's a homework due based on this, but I won't, I will extend it until after we get done with the example. So I will solve the example in class. I will go over the actual steps, and the homework problem is exactly the same as the solved example. So it shouldn't take you long to knock it out. Okay. All right. So have a good day. I will see you all on Friday. If you're in my lab, I'll see you today or I'll see you tomorrow. I'll be in my office later this afternoon. So if you have questions, come by.